Okay, so remember how we didn't finish the end of the ionization energy lab? I told you I was going to tell you about it. So here's kind of what your graph should look like, this picture that you can see on my screen. And I'm just going to show you, I'm going to talk to you about it a little bit. So one of the things they asked you to do were, number 11 says, are there any imperfections, exceptions to the trend? On your graph, circle all exceptions and label them with their element symbol. So you can see these are already labeled with the element symbols. Um, the ones that I want to highlight are, the ones that are exceptions. So it'd be like this lithium. Sorry, I guess I should circle it. Any of the dips. So boron, oxygen, sodium, aluminum. Oh my gosh, I can't make circles. Sorry, not with this pen thing. Sulfur and potassium. So there's a reason for all these dips. And the easiest way to say it is if you draw the electron configuration for them. And actually, maybe I'll draw them on the board back here. So let's just compare two of the smaller ones. Let's compare B versus BE. Let me erase this here. So boron versus beryllium. Okay, so here's boron versus beryllium. So what's the configuration? Let me move a little closer so you can see. So the configuration for boron, it just has 4 electrons. So it's going to be, 5 electrons, sorry. So it's going to be 1s2, 2s2, 2p1, right? That's boron. And then beryllium is going to be, it's just 3 electrons. So it's going to be 1s2, 2s1. Okay. So that's what that's what they look like. That's what their configurations are. And the trend should be for ionization energy. Remember, trend is it increases up and to the right. That's like the trend. So boron is on the periodic table like here, and beryllium's over here. So who would we, just based on the trend, who would we expect to have a higher ionization energy? We would expect it to be boron. But if you look at the actual graph here that we circled, it's not. Boron's actually lower. So why is that the case is what they're asking you. Okay. So if we talk about the configuration and we compare it, I'm just looking at the question, making sure that we answer it fully. It says, are there any imperfections? And those are the imperfections. And then examine the AFBAL, and you circled in 10, or that was actually an 11. So we're looking, this is talking about the electron configuration for this. So what makes it lower when it's not supposed to be? So we have a 2p1 and a 2s1. And boron's supposed to be higher, but this is even farther from the nucleus, right? The 2p1 is farther from the nucleus than the 2s1. This one is feeling a lot of pull from these electrons over here. And this one is going to have more shielding because these guys are in the way of this 1p. And the 1p is farther away from the nucleus, farther away from the proton's pull. So when it's farther away from the proton's pull, it's easier to pull that electron off. Because remember, that's ionization energy, energy it takes to remove it. Okay. Another thing we could look at is a difference between nitrogen and oxygen. See nitrogen and oxygen on here? It's up here. So nitrogen and oxygen. So again, let's look at that real quick. So on the periodic table, again, ionization energy increases up and to the right. And if we look at nitrogen and oxygen, it's literally they're right next to each other, nitrogen and oxygen. So we would expect oxygen to be higher. But if you look at the graph here, it's not. It's lower. So why is that? So if we write the configuration for those, nitrogen is 1s2, 2s2, 2p3, and then this is nitrogen. And then oxygen is going to be 1s2, 2s2, 2p4. Okay. So why is oxygen lower than nitrogen? I'm going to tell you why. So if we draw the configuration of these, and we're just going to draw the last level. So I'm going to draw that 2p. Remember, it's 3 blanks. You have 3 orbitals. And then same thing for this p. So for the p, I'm going to put in 3 electrons here. 1, 2, 3. And then for the p here, I'm going to do 1, 2, 3, 4. So it's it's nice to see it. You can see that how many electrons they have and if they're paired or not. So this one, nobody's paired. This one, we have somebody paired. In this pair, there's repulsion. Okay? So, because remember, electrons repel each other. So if you have two electrons side by side like that, they're going to repel and it makes it easier to remove. So that's why oxygen is lower than you'd expect it to be. All right, I hope that explains some things for you guys.